Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is going to be lecture number 51 and this is also tutorial number 13. So in tutorial 12, that is in the last lecture, we were discussing about the derivation of Boltzmann distribution in the context of how to understand local thermal equilibrium in astrochemistry. During the approximately past two tutorials, we were involved in deriving the Boltzmann distribution in detail. In other words, we paid attention to all the individual steps. But because there were a lot of individual steps and each of these steps involved a lot of mathematical and physical detailing, I thought that it would be a good idea to summarize all the steps. Okay, a briefly big picture qualitative summary of all the steps so that once you go back to the previous tutorials, you know exactly why what step is done. Okay, so on that note, we shall begin this tutorial. So the first question for today's tutorial session is therefore going to be provide a more or less qualitative, okay, right? More or less qualitative summary of all the steps involved in the derivation of the Boltzmann distribution that we saw in the last lecture. So this is what we shall be looking into now. Okay, so the answer shall be given right here. So what was the first step? The first step was to define the weight of a system, right? We defined the weight of a system. And what is the physical meaning of the weight? It kinds of tells you about the various ways in which all the molecules present in a system could be arranged. An indicator of W is an indicator of the number of ways in which the molecules present in a system could be arranged. And what was the formula we saw? We saw that my W is given by capital N factorial divided by N0 factorial, N1 factorial, N2 factorial, blah, 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 all the way up to as many a different number of energy states are there. Okay, well, N is the total number and my N0, N1, etc. are the number of molecules in each energy state. Okay, so you could go back to this expression from the previous tutorials and get more details about it. Okay, so we started off with this by defining the weight in this following way. Then what did we do? We then took the two conditions, okay, right? Two conditions that, okay, what were the two conditions? The two conditions were that the sum of the individual molecules in the energy states, right? In the various individual energy states, starting from I equal to 0, where Ni is the number of molecules in the ith energy state, right? To however many energy states are there, right? That is going to be equal to total number of molecules present, okay? And also that the total energy of the system, okay, is going to be given by the product of the number of molecules in each individual state times the energy of that state. Okay, that is going to be giving the total energy of the system. And because n is dimensionless, right, it's just a number of molecules. So here, of course, this thing corresponds to units of energy. All right, so these were the two conditions we saw, and we also saw that on top of these two conditions, we had to keep my n and d constant over time. That is, the total number of molecules and the total energy of the system were constant over time. In other words, okay, there could be individual fluctuations within, the different energy states of a molecule, right? However, the net energy of the system and the total number of molecules present, they always kept a constant. Are we clear, right? So this was condition number C. Now, what is the next condition? The next condition was that I shall delete. Sorry, not the next condition, the next step. So this was step A, where we defined the weight, and then we defined two conditions for the system in step B, and also that the n and d were constant, right? That is step C. So the next step is going to be, so we had to deal with W, which is the weight, but instead we were manipulating mathematically the expression for ln W. In other words, we were choosing to work with ln W, okay? So we were working with, part of working with ln W for ln W, that is the natural logarithm of this particular expression, ln W, right? And we also approximated it. See, because we had lots of factorials, it was mathematically easier to get rid of the factorials. So therefore, we started off with ln W, and after making an approximation, what was the approximation called? It was called the Stirling's approximation, STIR, Stirling's approximation. We got an expression for ln W. I'm not going to be wasting time by writing the same expression again and again. You can just go back to the exact expression we got. I'm just now providing a more or less qualitative summary of the steps. Okay, right? And by the way, so we manipulated W to get ln W. But why were we working with ln W? Well, we were working with ln W because, see, the actual reason goes back to macroscopic thermodynamics. Okay, ln W is associated with what is called as the entropy of a system, and our idea was to maximize the entropy of a system. But don't worry if you don't understand what my previous statement, the entropy meant. Okay, the only point I want to tell you is that our idea was to overall maximize W. Okay, right? In other words, we wanted to present the system with as many accessible states as possible and arrange them in as many ways. Okay, so to do that, we worked with ln W, that is like logarithm of W, natural logarithm of W, and we had to maximize it. Okay, right? I'll write it down here. That is point E. So having obtained the expression for ln W, we maximized ln W, right? We obtained the maxima for W subject to the conditions given in this in point B. Okay, right? That is, the total number of molecules is a constant and the total energy of the system is also a constant, such that the expressions for E and M are given here. Capital E and capital N are given over here. Okay, right? So we maximized ln W subject to the conditions in points B and C right here. Okay, so these were the conditions we used. Now, why did we maximize ln W? As I was telling you, right? One way to understand it is that we wanted to provide the system as many ways as possible to access all the possible states. Okay. In other words, more technically, this is called as maximization of entropy. Okay. However, don't be confused with the use of the word entropy, which I'm introducing for the first time perhaps in this course. Okay. It is coming from macroscopic thermodynamics, but I have not told you more details. Okay, don't worry about it. So we maximized ln W subject to these two conditions. What is the next step? While we maximized them subject to these two conditions, we had some expression, right? So then to ensure the dimensional meaningfulness of the equation. Okay, right? In other words, we had to maximize L and W subject to these two conditions. We would be getting some expression. What expression exactly? Again, please go back to tutorial 12 and maybe perhaps some part of tutorial 11 also, and you would be seeing the expression. Okay. Now, for that expression to be dimensionally meaningful, we had to introduce two terms, alpha and beta. Okay, right? So, as part of while maximizing L and W subject to B and C, for dimensional meaningfulness, that is right, for the equation to be dimensionally meaningful, we introduce two terms, alpha and beta. Okay, this is the Greek letter alpha, this is the Greek letter beta. Now this is the physics or chemistry version of it, that is for dimensional meaningfulness. Mathematically, what we are doing is we are introducing what are called as undetermined multipliers. Okay, now once again, don't worry about the exact technical jargon used. The idea is that the equation should be dimensionally meaningful subject to all these conditions. So therefore we are introducing two terms, alpha and beta. Okay, so after having introduced alpha and beta, what we did was, this is important. So the expression we obtained, right, as part of maximizing L and W was a partial differential equation. Okay, we had a partial differential equation after step F. Right? We had a partial differential equation. It was much more difficult to analytically solve. That is, solve by pen and paper. Okay. In order to, solve this equation, we made use of a very important and amazing, criterion to solve this. I don't think I went through the details for want of time. Okay, the exact solution I didn't do, but it can be very easily done by this particular step I'm talking about. Okay, right? I showed you a partial differential equation, and I told you that by making this connection, so many terms would vanish. It is very easy as a homework for you to do, as to how exactly the partial differential equation becomes an ordinary differential equation. Okay, right? So to solve it, but what was the overarching assumption? What was the overarching idea used? Not an assumption, it's a fact. The fact that we used was that the various Ni, right, and Nj's are independent from one another. Okay, right? So they are all independent of each other. So by using this idea, right, that what are the Ni's and Nj's I'm talking about? Well, recall sigma over I, n sub I is equal to capital N, right? So, in other words, the number of molecules present in each state is independent of one another. Okay, so that's a starting idea that we have for this problem. Okay, so using this idea, the partial differential equation that we had, right, it's simplified further. Okay, it's simplified further, and what we got was a routine differential equation, or an ordinary differential equation. Let's call this G sub 1. Okay, we just didn't do that. One more thing that we did, okay, right? One more thing we did was, see, this equation contains alpha and beta, right? We have like two terms here, correct? So as we had both alpha and beta, what we did was that we used the idea, sigma over I equals, I don't know, 0 to whatever is the upper limit, n sub I is equal to capital N. Sigma over I, n sub I is equal to n. We use this idea to get that alpha and beta could be interconnected. Okay, right? So to connect alpha and beta and expressed everything, okay? And expressed everything we have expressed the equation in terms of beta. So although we introduced two different parameters, alpha and beta, we found that they were not independent. And using this idea, right, we could connect alpha and beta. And so overall, we express the equation via only one parameter, beta. All right. So this is step number G. Okay. So far, starting from steps A to G, that is starting from the definition of weight all the way up to, getting an expression after having differentiated, maximizing L and W, and using the criterion that the conditions also have to be met, and then introducing alpha and beta, converting the partial differential equation to an ordinary differential equation, and connecting alpha and beta, expressing everything via beta. What we did so far was mathematically rigorous. Okay, please note it, right? So until step G, everything that we did was mathematically rigorous. Okay, now in step H, that is, okay, in the next step, right, we introduced, okay, right, we as an I, okay, I simply introduced beta equals 1 over kBt, right? I simply introduced, I did not derive, okay, I emphasize categorically, did not derive but merely told you, okay, right, merely told you, right, to take it for granted, okay, right, told you to take it for granted, okay. So we introduced beta equals 1 over kBt. All right, now why did I not derive it? Well, its actual derivation, involves much more knowledge in molecular thermodynamics and connecting it with statistical thermodynamics. In any case, we can only, rigorously show that my beta is inversely proportional to temperature, okay, right? Why the proportionality constant happens to be Kb is actually empirical, okay? Are you clear? So I'll also, I'll also state it here itself that, so note that, what am I saying? Yeah. So here, note beta is inversely proportional to the temperature, right, in Kelvin, can be shown from molecular thermodynamics and connecting it with statistical thermodynamics. That's the easier part, okay, but due to a want of time, we're not going to show that. Yet, that the proportionality constant, okay, that the constant is the Boltzmann constant, right? That is an empirical idea. Please note this, okay? So overall, right? So overall, this is how we obtain the Boltzmann distribution, starting from the idea of a local thermal equilibrium. By the way, while we are at point H, I must also tell you that because we assume local thermal equilibrium, one could define one unique temperature value for the system, okay? I mean, just note, I'll call this note 1 and note 2. Your step H is also valid. Step H is valid. I'll put it this way. Step H is valid also because one could initially, right? One could initially associate one temperature value for the system. Okay, right? One could uniquely define one temperature value for the system under local thermal equilibrium. Okay, that's the validity for this H. All right. So this is how we obtain the Boltzmann distribution. And what I gave you so far in this tutorial was a summary of each of the steps. Now, if you go back, right, go back and you may just reconcile each of the steps, the big picture involved in each of the steps with the exact details, so that you have a perfect understanding of what was actually done for the derivation of the Boltzmann distribution. All right. So on that note, I shall now proceed further. Okay. So the next question, in this tutorial is going to be, now we have some expression. We have the expression, let's say the expression we had was for the Boltzmann distribution. The expression, the Boltzmann distribution, I'll just call this BD, right? BD for Boltzmann distribution is given by Ni by n is equal to e to the power minus beta ei divided by sigma over I equal to 0 to whatever the upper state is, right? E to the power minus beta ei, with beta equals 1 over kBt. Now the next question, that we should be asking is, what is the relevance? What is the significance of the the numerator we understand, okay, right? It is just, the exponential, what are we exponentiating? We are exponentiating the energy of the ith state, which is multiplied by some constant, okay, right? That is the numerator. But the denominator is actually very special, okay? We shall be talking about it now. What is the significance of the denominator? I'm just going to call this Ni by n is also, we can call this as like numerator over denominator, okay, right? So what is the significance of this denominator? I mean, that is this particular term right here. I equal to 0, e to the power minus beta ei, right? And not just in astrochemistry, but also in physics, chemistry, etc. And I shall, probably in the next tutorial session, particularly highlight the significance of this term for astrochemistry, okay, right? Overall. So this question is that, what is the significance of the denominator overall, right? Its specific application in astrochemistry, not application, relevance in astrochemistry, I shall be highlighting in the next tutorial, okay? All right, so this is the question now. The answer, I'll first give you the big picture answer, right? And I'll justify the answer in a bit, okay? So the answer is that the denominator, that is this term containing the summation symbol, okay, right? Now the denominator is what is called as the partition function. Please, take this place to your heart, okay? Is what is called as the partition function for a system. So it's typically, denoted by Q or Z. I mean, capital or small, depending on the context, okay, right? It's denoted by Q or Z. For this course, maybe we'll be using the symbol Z, okay, right? Okay, so this is the partition function for a system. What does it signify? So the significance of the partition function is that the partition function Z, right? It provides information about the number of thermally accessible states at any given temperature, okay, right? Now if you look at this sentence, well, number you understand, some number, thermally accessible, that is, well, stuff that is accessible as a result of the thermal energy present in the system, right? And what about this phase state? By now, you should definitely have no confusion in this course about the use of the phrase state. What do I mean by state? Well, I'm talking about an energy state, right? We have, if you recall, probably, in a lot of earlier lectures, we are now used to understanding that a molecule has a rotational energy states, vibrational energy states, electronic energy states, etc., etc. Okay, so that is the state we're talking about here. And of course, at any given temperature, we understand temperature. So my partition function provides information about the number of thermally accessible states at any given temperature. I've given you the statement, but hey, it is highly unintuitive, right? After all, well, there is a sigma term over here, there is an exponential term over here, and there is this negative beta ei and all that. how do I physically make sense of this statement right here, right? I mean, all I'm trying to say is I have this mathematical term here, right? And I have made a statement about it. But how do I make the physical connection between this mathematical term and the statement that I'm making right here? Okay, right? So this needs to be justified, right? So in order to justify it, we'll do it this way, okay, right? So in order for us to justify the statement right here, right, that is the partition function gives a measure of the thermally accessible states to in any system at a given temperature. Let us consider, to justify the statement, let me just call this statement Z, okay, right? So to justify statement Z, consider extreme cases. What do I talk about extreme case? Well, what do I mean when I say extreme cases? So you go back to this expression right here, sigma I equal to 0 e to the power minus beta ei, okay, right? I'll write it down here again. Z equals sigma over I equals 0 e to the power minus beta ei, right? Now, first, consider, okay, beta tends to 0. Let's say beta tends to infinity, which means what? Because my beta is 1 over kBt, never forget that, right? Beta tends to infinity and t tends to 0, right? This is one extreme case. And what is the other extreme case? This is case 1. The other case is going to be beta tends to 0, which means my temperature tends to infinity. Okay, so by considering these two extreme cases, okay, we shall be justifying the statement right here that the partition function is a measure of the thermally accessible states at any given temperature. So this aspect, right, with this aspect, we shall be continuing in the next tutorial session. Okay, thank you so much. So what did we look into in this particular tutorial? Well, we were looking at a summary of all the steps involved, right, in the grand derivation, in the complete derivation of the Boltzmann distribution. Okay, because there were many details and it's easy to get lost in details. I gave you a summary of each of the steps involved, and followed by that, we shall be in the next tutorial looking at the significance of this particular term called as the partition function. Thank you so much. See you all in the next tutorial.